In this video, I'll go over some of the most common probability distributions that are used in quantitative modeling and see how they are implemented in Python. So let's start with the first one, the most common one, Bernoulli distribution. So Bernoulli distribution models a single trial with two possible outcomes, a success and a failure, with P being the probability of success. The most common example is the flipping of a coin. The probability mass function is given by P to the x times 1 minus P to the power 1 minus x, where x is either 0 or 1. So this is essentially saying probability that x is equal to 1 is P, and when probability that x equals to 0, this is 1 minus p. This probability of success p, and probability of failure is 1 minus p. This has a single parameter p, which is the probability of success. Some common questions pertaining to this are: what's the expectation and variance of Bernoulli? So the expected value is given by p, and the variance is p times 1 minus p. To calculate it, you can use the definition of expectation, which is x times p of x sum over all x. So here it's either 0 or 1. So 0 times 1 minus p, that's 0. So this will give you p. For variance, you can use the expression, this expected value of x square minus expected value of x whole square. This gives us the variance of x. And if you evaluate this, you'll get p times 1 minus p as a variance. How can you simulate a single coin toss in Python? We sample points from a Bernoulli distribution. As we'll see in the examples, we'll just see in a minute. How does Bernoulli relate to the binomial distribution? So Bernoulli is a special case of binomial. In binomial, we have n trials, and the distribution is the number of successes out of those trials. If we have a single trial, that is, if we take a binomial distribution and set n equal to 1, then we get a Bernoulli distribution. So here are some examples. We import the Bernoulli package from SciPy.stats. We set the parameter p equals to 0.7, which is the probability of success. To calculate the PMF at x equal to 0, we use the function Bernoulli.pmf and pass it. The first parameter is x and the second is p. So we pass it 0 and p. Similarly, for x equal to 1, we pass 1 and p. This gives us the PMF for 0 and 1. To sample 10 random points from the distribution, we use the function Bernoulli.rvs, and we pass the parameter p and size, the number of points that we want. So we want 10 Bernoulli trials, we pass it size equals to 10. The expectation and variance are given by the function Bernoulli.stats. This gives us the mean and the variance of the Bernoulli with parameter p. Next up is the binomial distribution. Binomial counts the number of successes in n independent Bernoulli trials, each with a probability p of success. For example, the number of heads in 10 coin tosses. The probability mass function is given by this expression, which is n choose k times p to the k times 1 minus p to the power n minus k. Now, where is this coming from? So it's very easy and intuitive to see. We have n trials. Out of those, we are choosing k for success, so we have chosen k for success. We put the probability p for those k, and for the remaining n minus k are failures. So probability 1 minus p for all of those n minus k remaining. So this becomes 1 minus p to the power n minus k. There are two parameters: the number of trials, and p, the probability of success per trial. And the number of trials, and p, the probability of success per trial. Some common questions: how do you compute the probability of getting at least 3 heads in 5 coin tosses? So we have to calculate probability that x is equal to 3 plus probability that x is equal to 4. Probability that x is equal to 4 plus probability that x is equal to 5. Add it up and we get the answer. We can also do it the other way, that is, calculate the ones less than 3 and in the end do 1 minus that number, which we get. What are the mean and variance of Bernoulli distribution? The mean is given by n times p, and the variance is given by n times p times 1 minus p. The derivation is also pretty straightforward. You just have to use two expressions. So first, for expected value, you have to use x times p of x summed over all x to get the mean expected value. And for variance, you have to use, let me just clean up the screen a bit. For variance, you have to use expected value of x squared minus expected value of x whole squared. How does Bernoulli relate to the Poisson distribution? So Poisson is a limiting case. Sorry, how does a binomial distribution relate to the Poisson distribution? Poisson is a limiting case of binomial. That is, when n tends to infinity and p tends to 0, such that np is lambda. In that case, this binomial would become a Poisson distribution. Now, in Python, SciPy.stats package, we have the binomial package. We import it from here. We set the parameters n as 10, p as 0.5, the probability of success, and the number of trials. To calculate the probability of exactly 3 successes, that is, we have to calculate probability that p of x is equal to 3. We have the same function that we saw previously, except that the names instead of Bernoulli is binom. So binom.pmf, the parameters passed are x, n, and p. So x is 3, we pass 3 here. Probability of x, at least 3 successes. So you can calculate the CDF up till 2, and then you do 1 minus the binomial CDF, we get the probability of at least 3 successes. To randomly sample, we use binom.rvs. We pass the parameters and the size, which is the number of samples that we want. So you'll notice here that the functions names are similar regardless of the distribution that we are uh, sampling from or calculating the CDF PMF for variance stats from. For mean and variance, we have again the same function binom.stats, pass the parameters n and p, and you get the mean and variance of the distribution. Poisson distribution models the number of events occurring in a fixed interval of time and space. So as we just discussed, Poisson is a limiting case of the binomial distribution. So it models the number of events occurring in time and space. For example, the number of trades per second on an exchange. Approximates the binomial when n is large, that is n tends to infinity, and p is small, and np is equal to lambda. The PMF is given by this expression, probably that x equal to k. The number of events is given by lambda, which is the average rate, to the power k times e to the minus lambda over k factorial. Now, each individual distributions can take a separate discussion altogether, and we can do a deep dive on each of them. But for this video, I'm just touching the surface of it and showing you how we can use the Python packages to do some basic operations that are useful in quantitative modeling. The parameter is lambda, which is the average rate of occurrence. Question: what's the probability of 2 trades in a second if the average rate is 3 trades per second? So we are given lambda is equal to 3, and what we have to find is what's the probability of 2 trades. So what's p x is equal to 2. So in this expression, we have k as 2 here, and we have lambda as 3. So this would become 3 to the power 2 times e to the power minus 3 over 2 factorial. How does Poisson distribution arise as a limit of binomial? So this arises when n tends to infinity and p tends to 0, and p equals lambda. Now, the derivation is rather lengthy, so I will not go into that part. But yeah, it starts with setting these limits in the binomial and then expanding it further. What are the properties of a Poisson process? So Poisson process, uh, usually denoted by NT, is a stochastic process that models that counts the events happening over time. Some of the properties are: first, it starts at 0, so n0 is 0. Second, NT is Poisson with parameter lambda t. Third is that every interval would be a Poisson process, Poisson distributed, which would depend only on the length of the interval. So what that means is n of, let's say, interval t plus h minus n T would be Poisson distribution with parameter lambda h. So in SciPy package, we have Poisson, SciPy.stats, we import Poisson, set the parameter lambda equals 3, which is the average rate, to calculate probability of exactly two events, that is P of x equal to 2. We use the PMF function, Poisson.pmf, 2 and lambda. Probability of at most two events, that is we have to calculate the CDF. So we have to calculate the CDF up till x is less than or equal to this part. So Poisson.cdf, we pass x2 and the parameter lambda. To sample points, we use Poisson.rvs, parameter lambda, and the number of points, that is the size. Mean and variance from Poisson.stats. Exponential distribution. So exponential models the waiting time between Poisson events. It is continuous and memoryless. A common example is the time until the next trade arrives. One of the key properties is the memorylessness property. And what this says is probability that t is greater than s plus t, given that t is greater than s, is the same as probability that t is greater than s. Now, to understand this with an example, consider that you have waited s time steps. You have already waited s time steps. What's the probability that you would wait another t time steps? So what this probability says is that this probability would be the same as you have not initially waited, which is to say you're starting from the beginning and just waiting t time steps and not having already waited s time steps. The probability density function is given by lambda e to the minus lambda x, parameter lambda. Explain the memorylessness property, common question. Why is it important? As we already just discussed, what's the memorylessness property here? How is exponential related to Poisson process? It's Poisson models counts the events, and exponential is the time between those two events. How would you simulate waiting time between trades? You would sample the points from an exponential distribution. Import the package expon set parameter lambda pdf at x equal to 1 exponential.pdf. The parameter here is scale, which is 1 over lambda. That's an important thing to note. Probability that x is greater than 2 is given by this function expon.sf. 2 and second parameter is scale. Randomly sample points RVS, parameter scale, and size. Note that we are not passing lambda as is, we are passing scale, which is 1 over lambda here. Mean and variance given by expon.stats, again scale is 1 over lambda. Uniform distribution models equal probability of all outcomes in a given interval. For example, random number between 0 and 1. Continuous or discrete with constant density. The PDF is given by 1 over b minus a, where x is between a and b. So a here, b here, and this is our uniform distribution. A is the lower bound and b is the upper bound. And this is constant over the range equal to 1 over b minus a. How do you generate a random float between 5 and 10? You sample these points between a uniform distribution between 5 and 10. Uh, Mean and variance. Mean is given by the midpoint of the range, which is a plus b by 2, and the variance is given by b minus a squared by 12. So b minus a squared by 12. We can import the uniform package from SciPy.stats as shown here. The parameters are a and b. The PDF at x equal to 7. The parameters are x, location, and scale. Location is given by the lower bound, and scale is the length, which is b minus a. Probability that x is less than 8 is given by uniform.cdf. Sample points, we use the same function, uniform.rvs, and specify the location, scale, and the number of points that you want to sample. Mean and variance given by uniform.stats. Now, finally, we have the Gaussian distribution, a normal distribution, which is one of the most common distributions used in modeling, and not just in quant modeling, but in pretty much every other area where you are modeling any phenomena. This The reason why it's so common is because of the central limit theorem, which says that regardless of what the underlying distribution or random variable has, the sampling distribution of sample means would always follow a normal distribution. The PDF is given by this formula over here, 1 over square root 2 by sigma squared e to the minus x minus mu whole squared over 2 sigma squared, where mu is the mean and sigma squared is the variance. What is the 95% confidence interval? For standard normal, it's 1.96 to 1 plus 1.96. How do you generate standard normal samples in Python? Same as we saw for all other distributions. State and explain the central limit theorem. We already just discussed it. How do you compute the probability that normal variable falls between two values? You calculate the CDF at both of these values and take the difference of those. So we import norm from SciPy.stats, parameters mu and sigma set to 1. For PDF, the function is norm.pdf to calculate PDF at x equal to 0. Probability that x is less than 1.96 norm.cdf, 1.96 mu and sigma. To calculate the probability between two different values, we calculate the CDF at these two values and take the difference of these. Randomly sample points using norm.rvs, pass the parameters and the number of points needed to find the mean and variance. We get it from norm.stats. So that pretty much covers the fundamentals of all the distributions and how to use them in a Python package using SciPy.stats package. So that's about it. That'll cover in this video. You can read more on this blog on datalooper.com/blog. There